Introduction. In this practice, we perform polymerase chain reactions for the previously extracted samples of DNA and RNA. Methodology. The first step was to let the DNA template, the buffer 10x, and the magnesium chloride of the Taq polymerase kit to room temperature so they can warm up, and they were put into ice again. The enzyme was to be kept always in ice until used, and after being used, refrigerated at minus 20 degrees Celsius. 3 PCRs were to be run, so a master mix was prepared using the calculations shown. After the thermocycles were determined, as shown, then, for the visualization of the PCRs and agarose gel, 0.8 and TVE 0.5x was utilized, and they were run at 110 volts for 50 minutes. Using the transluminator, we can read the results obtained for the product, and it's to be kept at minus 20 degrees Celsius for poster usage.
This fifth practice, we did PCR and we did an electrophoresis of our results. We didn't obtain what we expected, and maybe this is because we made a mistake while we were extracting the DNA. We confused the sample with the RNA sample, and we add trisyl to the DNA, and maybe this is why we didn't get a band in our electrophoresis. Because we didn't got the exact amount that we needed to have, so the primers could attach to this part and start elongating this part. We can see at the bottom the DNTPs and the primers that were in use, and we can see that that they weren't in a specific products form, because we can see heavy bands at the bottom.
The primers used had more than 40% GC, which is a good sign of their affinity and function. Also, their melting temperatures did not differ for more than 10 degrees Celsius. The alignment temperature was considered to be 66 degrees Celsius. The primers code for overlaps regions of two different genes, as we can see in the table shown at results, which make them degenerated if we wanted to amplify just a section of them. In our gel, we did not see correctly the bands. This is because an error during the extraction where some reactants were added to DNA incorrectly. Besides that, we cannot see the formation of inner-specific products, and that speaks well of the conditions that we kept the enzyme in. At the end of our gel, we can observe a bunch of material that was not used, and we infer that they are the DNTPs and primers that did not align correctly.
It is important to consider a series of conditions while doing the PCR. Knowing the kind of polymerase to be used is relevant to determine the optimal condition at which the reaction should be held. That polymerase was isolated from Thermus aquaticus, which is the most common use in standard PCR. This polymerase has exonuclease activity. The reaction should occur under a certain pH, which will be kept by the PCR buffer that is provided with each polymerase process. This buffer will give out the optimal pH and which polymerase work properly and which the primer align to their respective sequence. PCR is a technique commonly used for molecular biology analysis. It's very useful when a DNA sequence needs to be amplified to obtain a larger concentration. PCR requires basic components to be performed. A DNA template with a region that is going to be amplified, two primers, forward and reverse, Taq polymerase, DNTPs, and buffer solution. SIGN is a highly sensitive technique. Every step of the protocol has to be performed with the correct reaction, concentration, temperature, time, and the primary design. If these details are not respected, no specific product will be amplified, or the desired sequences won't be amplified.
In the third lane of our electrophoresis, we have our DNA. We could see two bands, but only one band is big and black. It's because all the DNA was concentrated there. Maybe because we have a mistake in the extraction and the primers couldn't add to the template to duplicate it, or maybe because we didn't immerse the DNTP solution and maybe these laws don't allow the DNA to duplicate correctly. The second lane is the positive control. It helps us to know the correct molecular weight of our sample and verifies the efficiency of the run. Herefore, we can appreciate very well the molecular weight because the bands are below the molecular marker. Finally, the first lane is the negative control. It has no template and helps us to know if our genetic material is contaminated with salts or proteins. No band should be visualized there. In our sample, we can appreciate a gray band in each lane. Probably there are the DNTPs and other materials like primers used to the PCR. Although something to recognize is that there is no contamination with salts or proteins in the sample. The PCR is a very useful technique that allows us to know the molecular weight of a sample. It's very important to purely realize a correct genetic material extraction that allow the primers to add to the template and do the amplification. During the PCR protocol, you need to be very careful with the proper amount of each component of the master mix and to immerse each one in the solution in order to avoid some losses.